Okay, here we go. Last time we were talking about the delightful topic of ergodicity. In summary, what we have is a situation where we don't have the luxury of taking an ensemble, rather we just have one realization of a stochastic process. We would like to evaluate different parameters of the stochastic process simply by examination of that one realization. Sometimes we can, sometimes we can't. If we can, for a specific parameter, the stochastic process is said to be ergodic for that parameter. Last time we spent a lot of time looking at a specific case for when the underlying stochastic process was stationary, and that we wanted to use that stationary process in order to evaluate the mean. What we decided after some computation was that the following was true, that if this equation were satisfied, that the time average representation for the mean of the stochastic process, well, I should say the time average converges to the mean of the stochastic process as t, the integral of integration, becomes very, very large. We saw that there were some stationary processes for which this wasn't applicable. The very simple case of the battery factory was not a case where the underlying process was ergodic. However, we saw for the random telegraph signal that indeed it was. Now, what we did last time was just for mean ergodicity. It's just for the mean. It doesn't mean if it's mean ergodic that it's distribution ergodic. It doesn't mean that it's in any other sense ergodic. And each of these different parameters or functions underlying the stochastic process has to be analyzed in of itself. So let's take a look at, well, let's see, these are the examples we're putting up on the screen of the telegraph signal where we said that was ergodic. And then we looked at the battery factory, and we found out that the battery factory was not ergodic. Now I'd like to look at autocorrelation ergodic. Because we can establish the mean out of a stochastic process does not mean necessarily that we can get the autocorrelation out of a stochastic process. So the question is, when for large t can we make the following approximation? I'm going to assume, by the way, that we know that the underlying stochastic process is wide-sense stationary. So the autocorrelation is just a function of the distance between the 2 points between them. So in this case, what we can do is we can take a time average of x of t minus tau. Now you look at this and it might be confusing. I think a nice way to think about this is as follows. Assume that tau is a fixed number so that you're only computing the autocorrelation for one value. You're computing the autocorrelation for one value. So what are you going to do? You will take x of t, then you will take x of t shifted, and you will multiply the two together and take the time average over a certain interval from minus t to t in order to estimate the autocorrelation for that value of tau, for that value of shift. Then for a different value of shift, you have to shift x of t over again, reevaluate that time average. And so for all of the different shifts, we can get estimates of all of the different values of the autocorrelation. So this is how we might estimate the autocorrelation from a single realization of a stochastic process, is by this approximation. We need to ask ourselves, much like we did for the mean, under what conditions can we do this? Under what conditions can we assume that the time average approaches the autocorrelation for that specific value of tau as t becomes very, very, very large? Actually, we've solved the problem already, although you don't know it. What we're going to do is we're going to find for a fixed tau, and again, this is the best way to think about it for a fixed tau. We're going to define y of t. We'll parameterize it by tau, but tau is just a fixed constant here. Then we're going to look at it for different values of tau. But for a fixed value of t, we'll define y of t is equal to x of t minus x times x of t minus tau. You'll notice this is the argument in the time average operation up here. Well, this is interesting. If indeed y of t is mean ergodic, then x of t is autocorrelation ergodic, right? So we can use the results that we obtained for mean ergodicity to apply to this case also. So x of t is thus correlation ergodic when y of t is mean ergodic, and it has to be mean ergodic for all values of tau. So if this process is mean ergodic, that means that the time average of this approaches its expected value, right? Well, what's the expected value of that? The expected value of this is the expected value of this, which is the autocorrelation. So again, if y of t is mean ergodic, then x of t is correlation ergodic. Well, that means that we can take our expression that we had previously for mean ergodicity, and every place we have an x, we stick a y and see what the consequences are. So let's go ahead and do that. And to do that, we'll need to compute the correlation, the autocovariance of the stochastic process y, because remember this went into the formula that we could use to evaluate whether it was mean ergodic. Well, notice that doing this assumes that y of t is stationary, wide sense stationary, right? Which doesn't follow necessarily from x of t being wide sense stationary, but indeed it could be. And so we have a bunch of things here. We have, if we substitute now for the expression for y of t, we get this. We substitute for this y of t shifted, we get this expression. And I think you can see that we have a pretty interesting situation. We have the expected value of a fourth order statistic. Remember that in order to characterize a stochastic process, we could characterize it 1 point at a time, 2 points at a time, 3 points at a time, which would give us a third order density function, a 4 points at a time. Well, this is a 4 points at a time parameter. And we have to assume, in order to evaluate the autocovariance of y, we have to evaluate this fourth order expectation of x. And you can see that's pretty ugly, right? Do you agree that's pretty ugly? Yes, that is ugly. Everybody agrees with me. So, establishment of correlation ergodicity thus requires fourth order moments of x of t. Don't forget, we're establishing the autocovariance ergodicity of this. So x of t, so therefore we need fourth order moments. And it's better than wide sense stationary. Just because x of t is wide sense stationary doesn't mean that y of t is. How about strict sense? If x of t is stationary in the strict sense, do you think y of t will be stationary in the strict sense? Yes. Yes, it will. Because everything in all orders have to be stationary in order for it to be stationary in the strict sense. So therefore, I point this out to show you that we can go to these different measures, but they get sloppy very, very quickly. And the nicest one that we have is the mean. And unfortunately, that's the simplest also. Any questions on that? Ergodicity, the ability to estimate parameters or underlying functions of random variables through one observation. Let me ask you a question. There was at one time a rage called median filters. You're familiar with median? How many are familiar with median filters in image processing? Okay, about 3 people. The idea of a median filter is very interesting. If you have, for example, a time series, and you have some outliers here, we're all familiar with moving windows, wherein with the moving windows we take the average as we move the windows along, kind of a autoregressive sort of process, a smoothing sort of process. The problem, or one of the problems with the moving window, is that if we have a very ugly outlier, that is a random variable that really goes to the top here, then as we move this along, this outlier is going to manifest itself and smooth itself over the reconstruction area. If you have a scenario where you don't want to use this outlier, instead of using the average, you use a different type of measure of central tendency, which is the median. So instead of taking the average of these, you take the median of these three. Well, the median of these three, of course, is this point, so that in the median filter you would obtain this point. And you would scoot it over, and the median would now be this point still, scoot it over, and you can see that as we begin to move this median filter over, that this really large outlier is totally ignored, right? Can you see that it's totally ignored? Whereas for an averaging process, it would be smeared throughout. So median filters are very nice. They were the rage, I don't know, 7, 8 years ago. There were actually companies that came out with median filters for television signals that were received over antennas, because they said that in these television signals that you would have things called sparklies. And what sparklies were little places in your TV, as if looks like I'm giving them measles. Sparklies are points in the television show where the pixels go to white. And you've all seen this as watching TV over an antenna. It doesn't come through digital cable. Okay, digital cable has no sparklies. But usually if you have an analog sort of communication system over an antenna or an analog cable, you will get these sparklies to a degree. There was a Purdue group that actually came out with a little chip that went through and did a median filter, and these sparklies are kind of like these big outliers, aren't they? And so the median filters were very, very nice and very good in terms of getting rid of that. Now, why do I go there? I go there because I'm going to get into something which was an algorithm which was used for performance of the median filter. And let's take a look at this algorithm. Suppose we had three numbers, 3, 2, and 4. Let's see, do I want to do 4? 5. Okay. We're going to do what is referred to as stack filters, or no, they're not stack filters, they're stack numbers, representations. It's a thermometer code for the representation of the signal. So do you see what I've done? I have 5 bits here in a row to recognize 5. I have 2 bits in my thermometer to recognize 2 and 3 for 3. You with me? Now, if we go through, something really interesting happens here. If we go and we obtain the median of these three, what's the median? The median is 3, clearly, right? Now let's go a row at a time. What's the median of 0, 0, and 1? 0. The median of 0, 0, 1, 0. The median of 1, 0, 1, 1, 1, 1, 1. You notice then that by going through each one of the rows, isn't that interesting? We come up with a thermometer representation for the median if we take the median of the 3 rows. Okay? This will also work if we want the minimum. What's the minimum of these two? It's 2, correct? The minimum is 2. So, suppose we go through this first row. What's the minimum here? 0. What's the minimum here? 0. Minimum here, 0. Minimum here is 1 and 1. And you notice that the minimum is 2 going through a row at a time. So one of the reasons that was put forth for this median filter, and one of the proponents of the chip design, was to use this binary representation for a median filter. I still don't think it's a good idea, because I think a thermometer code representation of a number is about the most inefficient way that you can do this. That you can do just about anything. Okay, but nevertheless, it's an interesting idea, isn't it? It's an interesting phenomena that indeed this happens. The question is, why does it happen? Anybody see why it happens? When we first do it, it kind of looks like magic, doesn't it? With the median and the minimum. The reason that we do it is that if we are to do a marginal representation of this, let's do a marginal representation over here, wherein we add up each one of the rows here, 1, 1, 2, 3, 3, we actually obtain a cumulative distribution function for the underlying numbers. It's an empirical cumulative distribution function, but nevertheless a cumulative distribution function. If you were to have a cumulative distribution function, say, that looked like this, and I were to ask you to find the median, how would you find the median? You would find the median by going to a half here, going over here and dropping down here, and that would be the median. Correct? This is exactly what we're doing in this sort of characterization. This indeed has an interpretation in a continuous fashion also. And the continuous fashion would be as follows. Suppose that we had some sort of process here, and we would like to evaluate, well, let me show you not its distribution, it's a straightforward generalization. Let me show you the density, how we could evaluate the density. One way to evaluate the density would be to go across here for all values of time, and then count the number of times that you went through a crossing, that you crossed the function, right? The number of times that you crossed the function. So you get a number here. We would go over here and take the number of times that it crossed the function. We would get a number here. We would go over here. We would get a number. And what we would do is we would be building a histogram over here. And this histogram would indeed be the underlying probability density function for this random variable. Now, it's a histogram, so we have to normalize it to get an area of 1. So therefore, if this were a Gaussian random variable, this would be a Gaussian probability density function. Okay? Now, you notice what we would do in practice is that we would have we would just look at things over an interval of the stochastic random variable from minus t to t. And we would be able to, from this interval from minus t to t, we could compute the histogram there, but it wouldn't be exact. What we would hope is that if the time interval that we looked at became infinite, that this would be exactly Gaussian in the limit, right? If it were, what would it be called? It would be called probability distribution function ergodic. In other words, we would be able to extract the probability density function from the underlying function, looking at one realization of the function. Over here, the median filter is taking advantage of kind of a pseudo distribution ergodicity. So these are different types of ergodicity. So we have looked at mean ergodicity in detail. We have shown that how that generalizes. We have shown how that generalizes to autocorrelation ergodicity. And now we have kind of waved our hands and showed how the concept of ergodicity can be applied to other concepts such as the probability density function. Now, could with all waveforms you do this? Well, the answer is no. It's always nice to go back to the battery factory. That disproves everything. The battery factory is not density function ergodic, because if you went to the battery factory and you looked at one realization, you'd have a single point out here, wouldn't you? Right, for the battery factory. So the battery factory is not probability density function ergodic. So I thought that would be an interesting sidelight for you. It was for me. Was it good for you? Okay. This leads us to the next chapter, analysis and processing of random signals. This is what we're interested in doing as engineers quite extensively. We will first talk about the concept of a power spectral density of a wide-sense stationary process. It turns out that the power spectral density of a wide-sense stationary stochastic process is the Fourier transform of its autocorrelation. There it is. S sub x of f is equal to the Fourier integral of the result. Now, what is interesting and isn't apparent just by looking at the Fourier transform of the autocorrelation is its properties. In fact, the following properties are kind of miraculous. They're kind of really interesting that it does happen, but indeed the following does happen. This becomes something which we refer to as a power spectral density. Let's parse the words, rightly divide the word. Spectral simply means it's a function of frequency. Power density Remember what probability density was? You integrated over it and you got probability. What do you think power density is? Power density, you integrate over it, you get power. So this is a power density that is a function of frequency. And if we were to integrate it over it, we would get power. So again, spectral means it's a function of frequency. Power density means integration over it gives it power. This is not obvious from simply looking at the definition of the Fourier transform of the autocorrelation, but on closer inspection, we will see that indeed this is the case. As with any case, we have with with any Fourier transform, we have the inverse Fourier transform. The inverse Fourier transform being given this way. Now, here's our claim to fame. Remember, spectral means a function of frequency. Power density is integration gives power. Notice what happens in this expression. Can you all see this expression or have it in your notes? This is one of the theorems of Fourier transform. If we set tau is equal to 0, this exponent goes to 0, and we're left with r sub x of 0, if we substitute tau is equal to 0, right? So we're going to evaluate this at tau is equal to 0. Doing so gives the integral over this power spectral density function being equal to the autocorrelation at the origin. Okay? Do you remember what we said the autocorrelation of the origin was? That was the power, the average power. So this reveals that if we integrate over this S function, that we do get power. So it is a power density. It is a power density. If we integrate over this function, we get power. The power spectral density has some properties. Let's talk about them. First of all is that the entire integral over the power spectral density is the total power associated with the stochastic process. That's what we just showed. It can also be shown to be an even signal in the sense that if we flip it around, we get exactly the same thing. Anybody ever figure out what negative frequency is? Anybody in here? Okay. I never have either. This follows from the fact that the correlation function is even. Have you seen the proof that the Fourier transform of an even function is even? Okay, let me elaborate on this. If you remember, we had the following situation. That the autocorrelation function was an even function. And now we're looking at the Fourier transform of it. So here's the Fourier transform of the power spectral density. None of my pins are giving me my desired degree of blackness here. Okay, so I've switched pins again. Let's see if this one works. Now you notice something interesting, and this is always true. Ooh, very nice. Okay, what we have done here is we have taken the Fourier kernel and we've divided it up into its Euler components, if you will. Now, I think you'll all agree with me that this is an even function and that this is an odd function, right? Classically odd. And now what we're doing is we are multiplying this function, which is an even function, and an even function times an even function is a even. An even function times an odd function is a, and what happens if we integrate over an odd function? Yes, the integral over any odd function is equal to 0. So therefore, the sign component here has no contribution to the underlying Fourier integral, and we're left with the following expression. For the power spectral density. You will notice that because the cosine is an even function, it immediately follows the following is true. It immediately follows that the following is true. That is, if we substitute a minus f in there, that's the same as a positive f, so the cosine stays the same, so it's exactly the same function. So therefore, this proves that the Fourier transform of an even function is itself an even function. And we should not say an even function. We should actually say real and even. Now, another thing which we can do here, which is kind of interesting, is recognize that this is a even function, that the integrand indeed is an even function, and that the integral from minus infinity to infinity of an even function is equal to twice times the integral from 0 to infinity of the even function, right? Since the negative half is exactly the same as the positive half. In that sense, a nice computational formula for the power spectral density is the following: 2 times this. So this turns out to be the second property of the Fourier transform of an even function. And because the autocorrelation is an even function, we see that from the overhead here that the power spectral density function is an even function. It's real. The power spectral density is real. You know, if you've taken any of the power courses, that we can have real and imaginary power, right? That's not the sort of power that we're talking about here. We're talking about all our power is going to be real. And this is actually manifest in the fact that S sub x, that the power spectral density is real. We will show this subsequently. We don't have the tools now to show that it's real, but we will. And that is also true for the power spectral density being greater than or equal to 0. I'm sorry, this is what we don't have the ability to show right now. This is obvious because the Fourier transform of a real even function is real. Fourier transform of a real even function is real. It is this one which says that the power spectral density is always greater than or equal to 0, is the one that we don't have the tools to show. We will show these very, very shortly. Shortly in terms of minutes. Proof to follow. Properties, both of them are real and even. Therefore, the following holds. This is exactly the expression that I put on the board for you. Since these are even functions, we can represent the power spectral density as twice the unilateral integral of the power spectral density times the cosine. We have seen that the power spectral density is such that if we integrate it over all frequency, we would get the total power. Suppose that we didn't want to know that. We didn't want the power from all frequencies. Rather, we wanted to compute the power in a band from B sub L to B sub U, L being lower, U being upper. So we have the situation, if you're watching the board here, is we have a power spectral density. It's real, positive, and even. And we want to compute the, let's see, I guess I'll use a capital L here, a lower bandwidth to an upper bandwidth. We want to compute the power of the stochastic process in this frequency band. The total power in that frequency band is equal to the area under the power spectral density. Almost. What is different is that because of the negative frequency idea of the Fourier transform, we also have to take the area here for negative frequency. So this area corresponds to the power in the frequency band from B sub L to B sub U. We simply integrate over one of the bands, and since it's an even function, this is the same as this, so we simply double it, right? And this is the expression indeed that we have over on the overhead, that the power in this particular band is equal to twice the integral from the lower limit to the upper limit of the power spectral density. Now, before we go forward, this is a very important concept because this explains why we call this a power spectral density. We know that if we integrate over all frequencies, we get the total power. If we integrate over a subband, we'll get the fraction of the power associated with the total stochastic process. When we talk about the stochastic process, what kind of stochastic processes are we talking about? Is the concept of the power spectral density applicable to every stochastic process? No. You remember the requirement was that the power spectral density was the Fourier transform of the autocorrelation. The double arrow is sometimes referring to a Fourier transform pair. This being the case, what is the assumption that we made here? By just writing this down in this fashion, we have assumed that the underlying stochastic process is wide-sense stationary. If it wasn't wide-sense stationary, we couldn't write this down. We'd have to write something like this. Right? Remember, it's a two-dimensional argument, and only for wide-sense stationary stochastic processes was it a function of the difference between the 2 points. So therefore, this autocorrelation is only applicable in the most general sense to wide-sense stationary stochastic processes. Because we're Fourier transforming this to a power spectral density, this power spectral density concept is only applicable to wide-sense stationary processes. So if someone comes to you with a process that isn't wide-sense stationary and asks you to evaluate the power spectral density, your response should be, the power spectral density doesn't exist in the classic sense. There are probably generalizations of the power spectral density, as there are for everything that you can apply, but in the strict sense, in the strict definition that we have here, the power spectral density is only applicable and only relevant to stationary processes. So therefore, we have narrowed our scope of stochastic processes that we have looked at, but in doing so, we've gotten some very powerful conceptual tools. There's a similar thing in circuit theory. To talk about frequency responses and Laplace transforms, you have to have linear time-invariant systems. And you'll notice the concept of time-invariant has the same flavor as stationary. A time-invariant system is a system that doesn't change with respect to time. If you have a resistor in it, that resistor stays exactly the same value over all values of time. So the system itself doesn't change with respect to time. The signals going in and out can change, but the system doesn't change. That's time-invariant. That has a similar sort of concept to the idea of wide-sense stationary, or stationarity, doesn't it? It means that the process doesn't change with respect to time. And we see a lot of parallel math here. Maybe you've noticed it, maybe you haven't. But there is a lot of parallel math. Okay, let's look at some specific cases. Let's look at the random telegraph signal. Remember the random telegraph signal? That had the autocorrelation here. We said that if we applied the flip theorem to the origin, that is, we flipped it over with a 50-50 chance, that this became a wide-sense stationary stochastic process, and that this was the autocorrelation of the stochastic process. If we were to do the Fourier transform, by the way, we have all the Fourier transform tools. It's exactly the same Fourier transforms we use for characteristic functions, but it's a different application. Don't get them confused with this. Fourier transforms are as common in engineering and physics as multiplication, if you will. They're just manifest in a number of different ways. Okay, so we have the autocorrelation function. It is for a wide-sense stationary stochastic process. Therefore, we can talk about the power spectral density. Power spectral density has a Cauchy shape, doesn't it? A Cauchy shape. And then if we would like to, for example, compute the power in a band, hour is kind of like power. from B sub L to B sub U, we use the expression that we offered before. Again, it's a power spectral density. So therefore, we integrate over the power spectral density. We integrate over the spectrum to get power. So it's twice times the integral over this, and now it's a little bit of integral calculus. It's twice, here's the expression for the power spectral density that we derived for the random telegraph signal, and as you can see here, it's the difference between two arctangents, since this integrand integrates to be an arctangent. So we can see that in this sort of fashion, if we have an analytic expression for the power spectral density, that we can apply such notions. The concept of the power spectral density is also applicable to discrete time signals. So let x sub n, you notice x sub n being a discrete signal, let it be wide sense stationary. The power spectral density is, well, for the continuous time stochastic process, it's the continuous time Fourier transform. For discrete time, it's a discrete time Fourier transform of the autocorrelation. So we have this expression then for the power spectral density. As in the case for discrete time and continuous time Fourier transforms, we always have to make a little disclaimer for the f here. Before, for the continuous time, f had units of reciprocal time. Here, f is unitless, just like in DFT sort of courses. So S sub x has a power spectral density properties, except that it has the same power spectral density properties as before. You integrate over an interval, you get power. The difference is that integration is restricted to be from minus 1/2 to 1/2. Now, if you're more into e to the minus j omega n, which is more of a standard way to do the discrete time Fourier transforms, this would be from minus pi to pi. Remember that the discrete time Fourier transform of any discrete signal is periodic with a period of 2 pi. Well, if you use f, the discrete time Fourier transform is periodic in the frequency domain with a period of 1. So like all discrete time Fourier transforms, S sub f, the power spectral density, is periodic with period 1. But it's also non-negative. It's also even. So it has all of the other property. Let's talk about some different types of power spectral density. And here are some which you might have heard of. We're going to talk about continuous white noise, discrete white noise, and then we'll talk about Laplace noise, which is a type of colored noise. Anything that is not considered to be white is referred to as colored noise. Continuous white noise, very interesting. Continuous white noise has an autocorrelation function equal to a Dirac delta. Therefore, its power spectral density is a constant, right? Because the Fourier transform of a delta is equal to a constant. But we got a problem, man, and that problem is as follows. If we look at this power spectral density as being a constant for all values of frequency, then if we're to integrate over this, we get the total power, right? And what is the total power? Yeah, it's infinite, isn't it? Much better. Okay. Wow. It's quite some power, right? By the way, is anything in the universe infinite? It's kind of a philosophical question. I haven't found anybody that's able to tell me that anything in the universe is infinite. Nothing in the universe, in the closed universe that we know about, is infinite. Anybody disagree? What do we mean as engineers and also physicists when we say infinite? We really mean it's our code for really, really big, right? That's what it means. This is also consistent with the idea that the average power is equal to the autocorrelation evaluated at the origin. Well, this turns out to be n naught over 2 times del of 0. And what is del of 0? If it's a Dirac delta, It's infinite. That's where the thing blows up. So we see we're consistent here. So in both cases, we get that the average power in white noise is infinite, which is weird, which means that white noise doesn't exist in its pure theoretical form. We call it white noise because if we go here, the spectrum is flat. And if we have in light all the elements of a wavelength or frequency, all the frequencies of a electromagnetic wave equally present, then we perceive this as white light, hence the name of white noise. So this is continuous white noise. Now, continuous white noise, why do we use it? We use it, one of the reasons is it's analytically great. You remember, for example, that we had the criterion for ergodicity? Let's see. Yeah. Remember, this was our mean ergodicity requirement? You recall that? Suppose we had zero mean white noise. If we had zero mean white noise, what would this be? N naught over 2 del of tau. You know what? This is a really easy integral to evaluate. And this is one of the reasons analytically why we like white noise, is because in expressions like this, which occur quite frequently in the analysis of stochastic phenomena, when we have white noise, analytic expressions, which are very ugly, simplify really nicely. We can here apply the sifting property of the Dirac delta, for example, and we can evaluate this thing at the origin. And what is this thing evaluated at the origin? 1, right? That tau is equal to 0. So this integral is nothing more than 1 over 2t. Again, delta functions, because of the sifting property of the delta functions, affect evaluations of integrals very easily. They're very easy to evaluate. So for here, we go to the value 1 over 2t immediately. This is one example. Autocorrelations appear in numbers of cases under integrals where if we had white noise, it simplifies things really, really nicely. So here's something interesting. Is white noise ergodic? Mean ergodic. What is the requirement? The limit of this must be 0 if what? Big T goes to infinity, right? Does this go to 0 when big T is infinity? Yeah, it sure does. White noise is mean ergodic. But we can't use something just because it's theoretically nice. The physical justification is that white noise is very, very close to the power spectral density of thermal noise. Thermal noise turns out to have a power spectral density which is flat over a very, very wide bandwidth before it begins to taper off. So as a good approximation, white noise can be used for thermal noise. The problem we've seen is that it has infinite power. And I don't think there's anything in the closed universe with infinite power. When we refer to white Gaussian noise, what do we mean? You'll hear this expression quite a bit because you remember Gaussian is also our friend, right? White noise is our friend because of the analytic simplicity of it. So therefore, if that's the case, then to be really friendly, we might talk about white Gaussian noise. White Gaussian noise means the following. Number one is that the autocorrelation, which is the measure between the 2 points here, is white. That means the expected value of any value of x of t times x of tau is equal to a constant times the delta function of the difference between them. So that's what we mean by white. You'll notice why a manifestation of this being infinite. Notice this is equal to 0. This correlation is 0 no matter how close we get the 2 points. We can get them with epsilon and they're not correlated, right? Here's an intuitive way to think about it. If they're not correlated when they're epsilon apart, it means that with the correlation measure that knowing one tells you nothing about the other one, right? They're uncorrelated, which means this next one, if it has nothing to do with this one, well, it could be up here, down here, anywhere, right? So therefore, in order to allow for those instantaneous jumps within epsilon of time, that's going to require infinite power, or lots of power, right? So that's one way that we can think about white noise, having infinite power. For the Gaussian part means that if we take the probability density function of any of the 2 points, then we will get a Gaussian probability density function. In other words, one of the things which we would expect is that if we did this integration like we did for the distribution probability density function ergodicity, that this would be a Gaussian curve here. That would be one of the manifestations for the Gaussian aspect. So this is what we mean by white Gaussian noise. You will hear this process, especially if you take courses in communication, because it's so nice as a simplifying assumption. You can have very complex equations, very complex concepts, and if you assume white Gaussian noise, you go boom, boom, and you get a nice answer. Whereas if you have any other type of noise, it's really ugly. Okay, discrete white noise is a different type of noise. We talked about continuous white noise. There's discrete white noise also. Discrete white noise occurs, we will see any time in MATLAB you generate a bunch of independent random variables and put them in a row. If you have a sequence of IID random variables, that turns out to be a discrete white noise process. So it means that the autocorrelation is equal to a value at the x bar squared times del of n, where this is now a Kronecker delta as opposed to a Dirac delta. It's a discrete impulse instead of a continuous impulse. The discrete time Fourier transform of that is x bar squared, which is also a constant. So just like for the continuous case, we have a nice continuous line. However, there's a difference between the discrete white and the continuous white. Number one is if we get the average power of the entire signal, we don't integrate from minus infinity to infinity. Remember, this is in general going to be periodic with a period of 1. So we get the total average power just integrating over a single period, which is from minus 1/2 to 1/2, for example. Another way to look at this is to recognize that for discrete white noise, that we have an autocorrelation equal to x bar squared over del of n. And you'll notice there's a reason that I use the second moment here. The Kronecker delta is equal to what at the origin? 1. Right, that's a definition of the Kronecker delta or the discrete impulse. That being the case, what is the autocorrelation at the origin? Well, it's equal to x bar squared, which we know is what happens anyway, right? So that's the reason that we use the notation of the second moment of the origin, because by default, that's what it becomes when it is evaluated at the origin. But if we have discrete white noise, you'll notice that an IID sequence, if we have an IID sequence, that is sufficient to be white noise, discrete white noise. It doesn't matter what the density function of these are. It doesn't matter if it's Gaussian, exponential, gamma, binomial, Bernoulli. Doesn't matter what the random variables are that you choose these. What's important is you just choose them as IID random variables. Then it turns out to be a discrete white noise process. By the way, you'll notice that writing this down assumes what? It assumes that the white noise is wide-sense stationary, right? Just by writing this down. So yes, indeed it is. So say that we had IID signals. If we have IID signals, what is the autocorrelation between two values of n and m? Well, it's equal to the expected value of x of n times x of m. If they're independent of each other, we know that we can break up this expectation of the product into the product of the expectations, right? So we can write this as follows. And this assumes that n is not equal to m, correct? This assumes that n is not equal to m. If n is equal to m, we get the second moment, right? So if we have an IID process, and there should be one more caveat that I put on there, which is zero mean. If it's zero mean, then this first term is always equal to 0, and we are left with, this is the autocorrelation, if we have a zero mean process. Okay? Here's something which is very important. Good qualifying exam question. We have finite power here. One might think that you can get discrete white noise points by sampling continuous white noise. And the answer is no, you can't, because that continuous white noise has infinite power and the discrete white noise has finite power. So the only time, if you were to sample white noise, what you would get is you would get discrete white noise where this second moment was infinite. So you can say in a degenerate case you would, but not in general. So you can't sample continuous white noise and get discrete white noise. Okay, are there any questions? If not, let's go take our break and have reconvene when the big hand's on the 6.
Bubble tea dry, though his pockets are empty, he still makes his mark. Just picking papers in the park.
Okay, last time we were also talking about the Wiener process in finance. And and when we talked about the Wiener process in finance, what we meant was the following. That we were going to do this and move with the hands, and the price of the security is this and this. This is the real-time streaming. That's actually pretty good, isn't it? Huh? The answer is yes. It's a real-time screening right off of the right off of this. We thought we could fool you, but I forgot about me coming in there. That kind of blew it, didn't it? Okay. Uh-oh. I think that the real-time video just screwed up Windows. Windows crashed? No. Okay, we might have to. You ever wonder how much time is wasted every day by people around the world waiting for Windows to boot? It's a lot, isn't it? Okay, do we have a hacker in the house? I'm hitting Control-Alt-Delete and nothing's happening. That's bad, right? Wait, I have the battery flashing. That's not good either. Okay, that's in there. That's in there. Well, I know of no alternative. Go ahead. Switch it off? Is that what the... any computer engineers in here? They wouldn't know, would they? Okay, let's go ahead and turn it off and reboot it. Okay. We're rebooting. Let's see if I can think of anything intelligent to say without my crib notes. What were you talking about? No. Not Wiener processes. Before the break. Before the break. I'm going to white noise and continuous white noise.
You're on your way to Laplace.
I was on my way to Laplace. Yes, I was. Okay. I'm sorry, I got distracted during the break and it put me off my game plan. Another type of noise, and is Laplace noise. And wait, I got to turn it back on, don't I? Okay. I just turned the computer back on. There we go. And with Laplace noise for the continuous case, we might have something like R sub x of tau is equal to x squared, the second moment, times e to the minus some value of say, t over t, for example. What do I have in the notes? Alpha t? In the notes? Anybody write the notes?
These aren't available online yet.
Yes, they are.
You got the old version.
This section of it isn't
Ooh, okay, that should not be true. Okay, I'll have to double check on that. Okay, by the way, extra credit. Everybody's been asking me for extra credit. I don't give extra credit, but I will this time because it'll be something that'll help me. If as of, what is today? Thursday. if as of Saturday you point out errors in the overheads to me, because that's difficult, because I'll be going along during the lecture. Hey, I got a problem, man. I don't know the password. Okay, it did it anyway. Anyway, if you hand in the actual printouts with pointing to where the errors are and what they should be corrected to, I'll give you a point for each one. Okay? Was that? A point. How much is a point? A point is worth a point. Let's see, a test point. That's too much, a test point. Quarter of a test point? Because there might be like 100. Let's say if I had 100 mistakes. If I had 100 mistakes, it would be 25 test points. Okay, quarter of a point.
The first one that gets it in?
Huh? Not everybody.
So if you get the same mistake, it gets...
Yeah, doesn't matter. Fifth of a point. Fifth of a point. Oh, guess what? I don't have Laplace noise here either. Okay, so you're right. Okay, Laplace noise is this. It has a. You'll notice for non-white noise, it's always nice to put this x bar squared out here in front, since you always know that the number that the autocorrelation evaluated at the origin is going to be x bar squared. And what is the power spectral density here? Well, it's something that we've figured out already. It's that Cauchy-looking thing, and that's an example for that's an example of Laplace noise. We did that already. You're playing with me. Okay, let's. Go to analysis and processing of random signals. You might remember, and you might not, at one time I mentioned that in the evaluation of stochastic processes that many times, not always, but many times for engineering applications, we could live not with the first, second, third, fourth, fifth, and sixth probability density function orders, but we could live with just the mean and the autocorrelation. And indeed, that's the truth. The reason is the following, and this is the problem that we're going to address here. If we are processing, in signal processing, noise which is wide sense stationary, the thing that we are interested in mostly is the second order statistics of it. We are interested, for example, in the average power in the noise. Why? So we can assess things such as signal to noise ratio, right? Because we need to know the energy or the power in the noise in order to assess signal to noise ratios. So if that, as engineers, what we're interested in, then the second order statistics are very, very nice. What we will find out is something very interesting. If we look at stochastic processes being fed into linear time invariant systems, which is something that we all know as engineers, then the output is going to be such that the first and second order statistics of the input can be mapped to the output. Therefore, if we know the mean and the autocorrelation of the input, we know the impulse response of the linear time invariant system, then we can compute the mean and the autocorrelation of the output. So we can follow these second order statistics through. And if what we're interested in are things such as average power and such, that means we can follow the power through also. And so we can assess things such as signal to noise ratio. So this is the topic of this last chapter, which we'll have time to cover this quarter, and that's the analysis and processing of random signals and filtering the random processes. Here's the concept that we will talk about. Do you have these notes? Yes, okay, fine. Do you have these notes? We have a linear system, and we have an input x of t and an output y of t. Now, linearity means, if you recall, additivity and homogeneity. We talked about the expectation operator being a linear operator. In general, y of t is equal to L operating on x of t, where L is a linear operator. Additivity means the response of the sum is the sum of the responses. Homogeneity means if you triple the input, you triple the output. That if you amplify the input, the output is amplified by the same amount. Such systems are said to be linear. If we have a stochastic input into a deterministic linear system, now you notice that we could model linear systems as stochastic. Maybe, for example, you have some resistor in there which is being hit by cosmic rays, and the resistor changes its resistance according to how many cosmic rays it hits. That would be a stochastic system. We're not going to assume that. We'll assume deterministic systems. For linear systems, and by the way, they need not even be time invariant. They can be a linear system where the resistor is changing with respect to time. That's okay. So just a linear system. For such systems, the expectation of the linear operators commute. It's a very important theorem. It's shown in your book in detail, and is actually something which isn't too difficult to prove. In other words, the expected value of the output, which can be written as the expected value of the linear operation on the input, is the same as the linear operation on the expectation. In other words, the linear operator and the expectation value operator commute. They're commutative operators. Is it true that linear operators always commute? Anybody know? They teach you this first quarter quantum mechanics. Can you think of two linear operators that don't commute? Well, Fourier transform is a linear operator. Shifting is a linear operator. If you shift in Fourier transform, is that the same as Fourier transforming and shifting? No. No. So in general, linear operators do not commute. However, expectation does commute, because expectation is a simple integral sort of operator, and we do have this very important relationship. So with that under our belt, that's for general linear systems. If we proceed to the analysis and processing of random signals, if we have a deterministic input and a deterministic LTI signal, now we are imposing the concept of linear time or time invariance. That is, that the system itself is not changing with respect to time. It's not a dynamic system. If we were to have a deterministic input into the system, we know that the input-output relationship is characterized by a convolution integral. This same relationship is used, and we've seen this before, that this convolution can be evaluated in the frequency domain as a Fourier transform. And what is h of f called? That's the frequency response of the system. If we had a stochastic input into a deterministic LTI signal, then the convolution property still holds. The only difference is that the input now is a stochastic process, which we'll call capital X of t. Now, capital X of t is such that that is the input to the system. It goes into the linear time invariant system, which is characterized by its impulse response, and that is equal to the output. So therefore, if we do have a stochastic input to a deterministic linear time invariant system, the input-output relationship is given by this. We might be tempted in such a case to do what we did with the deterministic inputs, simply take the Fourier transform of both sides. However, there's a kind of a challenge in generally taking Fourier transforms of wide-sense stationary stochastic processes. The reason is that these wide-sense stationary stochastic processes have infinite energy, don't they? If you take a wide-sense stationary stochastic process, let's remember what it was. It went on from minus infinity, 0, and on to infinity, right? Imagine now computing the energy in that signal. You square it, So everything flips above the axis, and you take the integral of it. Doesn't matter what that stochastic process is. What's that integral going to be? It's going to be infinite, isn't it? You can't take any signal other than zero, other than something identically zero, and square it and integrate over it. And if that is a stationary process, that is always going to be infinite. Do you agree with that? That was stochastic. Okay. That was cute. Hey, put me up here. Put me up there.
It's quite more complicated than it looks.
Oh, it is. It's the same with my lectures. Okay. Did you do? No, I did that. Okay. Yeah, there we go. I forgot what I was talking about again. The short-term memory goes really quickly. Let me draw a picture. We have a wide-sense stationary stochastic process. It's the same yesterday, today, and tomorrow. This is x of t. Now what we're going to do is we're going to square it. Don't forget this goes on for negative time all the way back to the Big Bang. And now we're going to square it. And it goes on towards... Did you read the thing in Time magazine where they found out the universe is flat and it's going to keep on expanding and pretty soon atoms are going to be the size of the universe? It was in Time magazine. Anybody see that? So this will go on to when atoms are the size of the universe. Really weird stuff. Anyway, that's the idea. That's the reason that nothing is infinite or... What's the other word? What means time for infinite? Forever. Okay, everything's finite. Now, if we did this, and we're going back into our little fantasy world of minus infinity to infinity, what is the total energy of this signal corresponding to the total area of this rectification? What's it equal to? It's an infinite, right? So it's infinite energy. So we get problems when we take Fourier transforms of things with infinite energy. I don't know if you've noticed that before. But a sinusoid, for example, has infinite energy, doesn't it? And what is its Fourier transform? A couple of delta functions, right? So in other words, you start getting into singularities and these very strange distributions when you begin to Fourier transform things with infinite energy. So for that reason, we kind of shy away from that. You can do it, and there's theories for it, but we rather, instead of look at the characterization through Fourier analysis, we do it a little bit differently, as you'll see. Let's first of all look at the non-stationary case. We have a linear time invariant system and a non-stationary case. By the way, notice we're going from very large to very specific. This is a linear time invariant system with an arbitrary stochastic process as the input. Over here, we have a linear time invariant system, and now we are going to talk about the general non-stationary case. And to do that, we would like to do a couple of things. We would like to trace the autocorrelation of the input to the output. If we know the autocorrelation of the input, how can we determine the autocorrelation of the output given the linear time invariant system? How do we do that? How do we do that? Well, here's the way we do that. First thing we do is to compute. First thing we can do is compute the cross correlation between the input and the output. So this is the expectation. And by the way, for all linear system analysis, including solution to stochastic differential equations, the approach that I'm going to give you is a specific manifestation of a more general approach, which is to first find the cross correlation and then use the cross correlation of the input and the output. Use that to find the correlation of the output by itself. Okay? So here is the cross correlation between the input and the output. The input and the, do you think the input and the output be correlated? Yeah, they better have something to do with each other. So yeah, you would expect that they would be correlated. So here is the correlation of the input and the output as a function of t and tau. Notice there's no assumption of wide sense stationarity. It's the expected value of x times y, and of course y is equal to x convolved with h. And here is, well, let's see, we simply write out this convolution integral. So we've taken this expression and written it out, and then we take the expectation. The only thing that's stochastic is this x of t and this x of alpha. This h is assumed to be deterministic. So when we take the expectation of xt, x alpha, what do we get? We get the autocorrelation of the input, don't we? We obtain the autocorrelation of the input, and then that is convolved in the variable tau with h of t. So the final relationship, which is very interesting, is that in order to get the cross correlation, we kind of fix t in terms of the input variable. We fix t, and we look at tau as our variable. We convolve with respect to the second variable in order to get the cross correlation. So this is, again, in general, linear time invariant system for any input. Wiener processes, telegraph signals, Poisson counting processes, it doesn't matter what. This is the relationship between the input and the output. Now, let's take the second step. Remember I said it's a general methodology. First cross, then the autocorrelation of the output. We're going to compute the autocorrelation of the output now, which is the expectation of y times y. And of course, this y is equal to x convolved with h. We just bring down this other value. This, by the way, should be a tau instead of a t. There's a fifth of a point if I don't change it. Okay. If we write this out in longhand, we obtain this, and you'll notice what we get. The only thing stochastic here is x and y. So when we perform the expectation, what do we get? We get the cross correlation, which we computed on the previous screen. Again, a general methodology. First compute the cross correlation, and then use the cross correlation to compute the autocorrelation of the output. And so this is the relationship that we have. So we computed this on the previous screen. We convolve it with h sub t. We convolve now in the t variable. We hold tau constant, convolve in the t variable, and that gives us the autocorrelation of the output. So here's the expression that we had. The output autocorrelation is equal to the impulse response convolved in the first variable with the cross correlation. That the cross correlation was equal to the autocorrelation of the input convolved with in the second variable with the impulse response. That looks like a repeat of the first equation. So a little repetition in your learning here. It shouldn't be there. It shouldn't be there. But the important point is this, another fifth of a point, if I don't get this changed. I see the points are just racking up here. R sub y of t and tau then is, this is the relationship that we have in terms of the input autocorrelation. We convolve it with h of tau, then we convolve it with h of t. This, by the way, is a very common sort of DSP sort of operation for when you have separable operations. If you were performing this digitally, what you would do is you would take the r sub x of t and tau, where, for example, the variable t ran this way and the variable tau ran this way. And what's the first thing you do? Is you perform a convolution of this with what? With respect to the tau variable. With respect to the tau variable means you take each one of these rows and you treat it like a signal and you convolve it with h of tau. You would take this row and you could convolve it with h of tau. So each one of the different rows is convolved with h of tau, because when you look at a given row, that means the t is fixed, right? So we would convolve each one of the, I've been saying rows, of course I mean columns. Columns go up and down, rows go this way. So we convolve each one of the columns. Now in doing so, what we would get is another matrix, right? In fact, what is this matrix? This is r sub xy of t and tau, where t goes this way and tau goes this way, right? What do you think we do now? We run each one of the rows through h of t. So we convolve this first row with h of t, second row with h of t, all of the rows with h of t, and then we get another matrix over here, which is off the screen, which is going to be r sub x of t and tau. So this is what the math is telling us to do. Does this remind you of anything? This is almost like doing two-dimensional DFTs, right? Because if you do two-dimensional DFTs of an image, you DFT one row, then you DFT another row. Question? Oh, I goofed. What did I do?
The results of yours.
Oh, the result is r sub y. Thank you. Yes. So this is what that math is telling us, and this is kind of a geometrical interpretation, matrix sort of representation of exactly what we're doing. Let's look at an interesting idea, and that's the differentiation of random processes. I think these are all out of order. Suppose that y of t is equal to the derivative of x of t. By the way, not all random variable or stochastic processes are differentiable. It's dealt with in your book, but we won't go into the details. Let's assume that it's differentiable, and we perform a derivative of it. The question is what is the relationship between the autocorrelation of the input and of the output? Y of t is equal to dx dt. Well, again, what do? We take the autocorrelation of the input, and we run it through the system with respect to the second variable. In this case, that corresponds to performing a derivative with respect to tau. That would be equivalent to running it through. By the way, what is the frequency response for this operation? What is h of t? I don't know what h of t is. What's h of omega or h of f? It's equal to j2 pi f, right? Because if you multiply the Fourier transform by j omega, you differentiate the function. Correct? Go like that. If you multiply by, that's a derivative theorem of the Fourier transform theorem, right? Do you remember that? Is it too late in the day, too late in the quarter? Come on, respond to me. Give me feedback. I'll give you all low grades if you don't. I see that you responded. See, it works. No, I wouldn't do that. It was just an idle threat. Hey, there I am. How you doing? Okay, so we take this derivative. Oh. You know how hard that is? Do you ever try to comb your hair looking at yourself in a TV monitor as opposed to a mirror? Because it flips to the left and right. It's really strange. Okay, so we take this derivative, and we evaluate it in this fashion in order to differentiate with respect to tau. Okay? And now what do? In order to get y, we operate on this with respect to the t variable. So we differentiate with respect to t, and we get this result. And so the overall output is this, that the autocorrelation of the output for a derivative, the autocorrelation of the derivative is equal to the partial with respect to t and tau of the autocorrelation of the input. Kind of cool. And here's the point that I was making in trying to get your response. If we were to take a function x of t and we were to run it through a system in order to get dx dt as the output, then the frequency response of the system, the linear time invariant system, would be j2 pi f, or in the parlance of omega talk, it would be just multiplying it by j omega. That's the derivative theorem of Fourier transforms. Remember that? That if x Fourier transforms to big X, then the derivative of x corresponds to j omega times x. So maybe you realize that. What's the impulse response for that? Anybody know? It's ugly. Something called a doublet, which is, you think delta functions are weird. The impulse response for this is something called a doublet, which is the derative of the Dirac delta. Oh my gosh. Dirac delta, of course, is weird enough itself, but talking about the derivative is very, very strange. But people do it, and it's referred to as a doublet. So that turns out to be the impulse response of differentiation, and it makes a lot of sense. You want to know why it makes sense? Because if you take a delta function and you differentiate it, what do you get? You get something that goes up to infinity, and then it goes back down to minus infinity for the other side, right? Right? And what you're doing then is you're convolving this doublet with the signal. Well, if you have a signal like this and you do the doublet, the flip and shift, of course, you get this. Well, what is that? That's this value minus this value, and then you divide by the differential. That's the definition of a derivative. You take 2 points, very, very close to each other, and you subtract them and divide by the difference between them. So the doublet kind of makes sense, but it has very strange analytic properties. So suffice it to say that the frequency response for differentiation is j omega, and forget the doublets. They're pretty ugly. So that's a differentiation of a random process. Any questions on that? You know what I'm going to do? I'm going to actually, because of time, skip over stochastic differential equations, which we'll return to them. But I'm going to go to the filtering of wide-sense stationary stochastic processes now, because this is of more fundamental interest than is stochastic differential equations. Here's the interesting result. When we filter a wide-sense stationary stochastic process, if we put a wide-sense stationary stochastic process through a linear time-invariant system, the output is also going to be wide-sense stationary. Now just reason with me and see if indeed this makes sense. And indeed it does make sense. We have an x of t here. It's the same yesterday, today, and tomorrow. We put this into a linear time-invariant system. What does time-invariant mean? It means that that system was the same yesterday, today, and tomorrow, right? That there's none of the parameters, the impulse response, nothing's changed. It just kind of is boring. It stays there. Well, if you have something which kind of stays the same going into a system that always stays the same, what do you think the output is going to be? Isn't that going to be something which always kind of remains the same also? That the output is going to be the same yesterday, today, and tomorrow, right? And indeed, that's the case. And what we will show is that x of t, if x of t is wide-sense stationary, we will show that the output y of t is also wide-sense stationary. And we will furthermore show the relationships between the two. Here's what we will show. Okay, I'm just going to advertise what we'll show. That the expected value of the output, which is a constant, is equal to h of 0 times x bar, where h of f is the frequency response of the system. In other words, the Fourier transform of the impulse response. Okay? That's number one thing we'll show. The second thing we'll show is that the power spectral density of the output is equal to the magnitude squared of the frequency response times the power spectral density of the input. These are the two expressions that we'll show. So this allows, again, us to monitor the second-order statistics of stochastic processes as they move through linear time-invariant systems. So if I have a number of these cascaded, I can look at the composite results, and everything will be wide-sense stationary. And this is the result. These are the results that I use. Now you will notice that this has the flavor. This has the flavor of the Fourier transform of the output equal to the frequency response times the Fourier transform of the input. It kind of has that flavor, doesn't it? Except we said that we couldn't do that. Well, we said we should maybe not do that because the stochastic processes that were wide-sense stationary had an infinite amount of energy, which isn't good, right? So, but this captures the same exact flavor in a very, very nice way and it captures the input-output relationship. And of course, once we get this, we can obtain the autocorrelations for the input or output simply by an inverse Fourier transform. Correct? You'll notice a couple of things too. Remember, this is a strictly non-negative function. Well, in general, the frequency response can be complex, right? So taking this magnitude squared gets rid of this complexity. This is a little sanity check we can do on this. Again, the output has to be non-negative. Well, H in general can be complex, not let alone negative. It can be negative. It can have e to the j's in it. But if we take the magnitude of it, that makes it non-negative. And we multiply one non-negative number by another non-negative number, and we get another non-negative number. Also, the magnitude of the Fourier transform of anything that's real is always even. Fourier transform of anything that's real is even. I'm sorry, the magnitude of the Fourier transform of anything that's real is even. So therefore, this magnitude is even. So if this is even and this is even, that's even too. So all of the properties of the power spectral density are very, very nicely preserved in this expression. And these are the actual important expressions that we want to use for, again, tracing a wide-sense stationary stochastic process through a linear time invariant system. So with that, let's cut the chit-chat and dig into the math. The expected value of y of t, which is the output, is equal to the expected value of the input convolved with the impulse response, and this is the convolution integral written out. Expectation commutes with integration, and so we have this as the expectation. The only thing stochastic here is this x of t. So this becomes what? The mean of the stochastic process. This expected value is just a constant, correct? And this is the constant that we can factor outside. We do that and we call it m sub x. We could have called that x sub bar. Your book calls it m sub x. I call it x sub bar. It says tomato, I say tomato. So this is the book representation of the mean. And then what we're left with is the integral of the thing shifted. Well, this is the area under the impulse response. And I tell you what, if you're doing the area under the impulse response, it doesn't matter if it's shifted or non-shifted. I don't care where you align it on the axis. If I integrate from minus infinity to infinity, I'm going to get the same thing. So that's indeed what I do here. I integrate from minus infinity to infinity. But you'll recognize that this integral is equal to the frequency response evaluated at the origin. Right? This is this theorem that we used before. If you evaluate the frequency variable, well, in this case, yeah, the frequency variable at the origin, you get the integral of what you're Fourier transforming. So indeed, what we have shown is the first expression, that the expected value of the output is equal to the mean of the input times the frequency response of the value at the origin. Suppose we were doing a Fourier transform. What's the frequency response of a Fourier transform? What's the frequency response of a Fourier transform? What's the frequency response of a Fourier transform? I embarrass myself. What's the frequency response of a derivative? That's what I meant to say. Didn't you understand? What's the frequency response of a derivative? J omega. What's that frequency response evaluated at the origin? 0. Which means if you run any wide-sense stationary stochastic process into a differentiator, what's the expected value of the output? Always 0. Doesn't that make sense? If you take the derivative of anything that's constant, which is kind of what the mean is, you remove that constant when you take a derivative. You're removing that DC value on that derivative operation. So it makes all the sense in the world. So if, again, you differentiate any wide-sense stationary stochastic process, the output has a mean which is 0. Again, we come back to the interesting, wonderful conclusion that if the input to a linear time invariant system is wide-sense stationary, so is the output. We have established part 1 of this, which is if the input is a constant, the output is a constant. Now we have to establish if the input has an autocorrelation which is a function only of the difference between 2 points, then the output has that same characterization. Okay? What does that mean? Is that a gang symbol or something? Anybody know? Okay, never mind. I don't want to know. Maybe I don't want to know. Okay, so let's do that. We're looking then at the autocorrelation of the output as a function of the input. So the autocorrelation of the output is equal to the expected value of y of t times y of t plus tau. Oh, this is what we're questioning. Is this true? Is the expected value of y of t plus tau only a function of tau? In other words, it's not a function of t anymore. That's what we're trying to establish. Here's the math. Okay, here we go. The expected value of this autocorrelation, we substitute in the convolutional relationships in terms of the inputs for the y of t and the y of t plus tau here. Then we bring in the expected values, we shuffle the integrals together, and the only thing that's really stochastic here is this x and this x, so we have this relationship here, but you look at that, and that's nothing more than a autocorrelation function. That's the autocorrelation function of x. It has some weird variables, but it's simply the autocorrelation function. And if we assume that the input is wide-sense stationarity, this expected value of the of these two values is equal to this should be an r sub x. That should be an r sub x there, r sub x of tau plus alpha minus beta times h of t, h of beta, d beta, d alpha. So this is the relationship that we obtain by simply performing the operations of convolution applied to the definition of the output autocorrelation. And here we're done. The output, again, that should be an x. The output is not a function of t. Actually, because we were able to combine these, and by the assumption of the wide-sense stationarity of the input, we were able to determine that the t values actually went away because of the autocorrelation of the input. We're left with an expression that's not a function of t. That proves the output is wide-sense stationary. Still doesn't show how we get the autocorrelation of the output except by this formula, which is a little bit ugly. The final result, if we were to evaluate that integral a little bit more precisely, is the results that I gave you initially at the beginning of class, or at the beginning of the sequence of lectures on power spectral densities, that the output power spectral density is equal to the input power spectral density times the magnitude squared of the frequency response, and also the expression for the mean. So this is how we trace wide-sense stationary stochastic processes through linear time invariant systems. We also have a case now of wide-sense stationary random processes for discrete time signals, because we have linear time invariant systems. We're obligated to do that. In such a case, the following relationships hold. The derivations are very, very similar to that for the continuous time. The expected value of y is equal to m sub x times h sub o. And the input-output relationship for the power spectral densities is the same exact math that we had for the continuous case. The output is equal to the input times the magnitude squared of the frequency response. Suppose that we had zero mean white noise, which was as the input. Well, if it has zero mean input, always if it's zero mean input, what's the output? Zero. By the way, if you have a linear time invariant system, we're talking deterministic now, and you put in a value of 0, do you always have to have an output of 0? Yeah, it's kind of like that. It has that same flavor, doesn't it? If the expected value of the input is 0, the expected value of the output is going to be 0. And as far as the frequency response, well, since the input frequency response is just n0 over 2, the output power spectral density is just going to be equal to the magnitude squared of the linear time invariant system, right? We can, of course, talk about high-pass and low-pass filters. I tell you what, I think I'm going to stop here and probably finish with some final concluding remarks on this. How many do we have left here? How many slides do we have left? Okay, we'll finish those 4 slides next Tuesday, and then we'll reserve the rest of the time for asking any questions which you have over the material for the final examination. I'll say a few words about the final. Is there any questions? Okay, hearing none, I dismiss the class. Thank you for coming.